is the beginning of my understanding of acoustics. And that is that if you really want to be a good acoustical designer, you have to develop an understanding of the relationship between how we perceive sound and architecture. For some people, that's just a straight, they look at the space, they know it. Russell Johnson, who taught me acoustics and was a great concert hall designer, he didn't know any mathematics or any acoustical measurement at all, but he was able to say, if we move this wall this way and get more sound from the side, he was able to put himself in these spaces and move them around in his head. It was pretty unbelievable. But for the rest of us, acoustical measurement and prediction really gives you a path to understanding what you're hearing and what the room is doing. Russell summarized this two different ways. The first way was you don't do acoustics to a room, you design a room for the acoustics needed. And then he later just said, acoustics is architecture, which was good for him because he was a Yale-trained architect. Acoustics is a challenging field because ultimately our understanding and our entire process is based on subjective criteria. And what we do by making measurements is two things. People thought you were trying to come up with target numbers. I'm less interested in target numbers than understanding how different methodologies in architecture apply to the methodologies of acoustics based on being able to predict what will result. This is a modern control room in a rustic setting. It's out in the countryside. It's about 2 hours north of New York City. It's called The Woods, and it's a beautiful, beautiful location. And the reason I show you this room is it's hard to know what era this room is from. It doesn't have many of the telltale signs of older rooms, and it doesn't look modern because of its rustic nature. Also because it has 2 analog consoles. This particular room is going to be transformed into an Atmos room next year, but it's set up for stereo monitoring. So I thought what I do is take a look at the design elements that go into a room like this. This is the live room, and obviously that's the control room. At the front, we have a large acoustical soffit that goes around 3 walls of this room. It comes across this wall. This gray soffit has no chipboard. It's just acoustical materials, ductwork, and some lighting. It also gives us a way to get cables moved around, hidden. In this case, we do have a basement we could drop down into for cable management as well. This was when we were setting up and testing the room, and you can see the daytime that there's natural light from a window to mixed left. There's natural light both from the window behind us reflecting slightly in the glass and some windows to the outdoors in the live room. So natural light was an important parameter. This part of the ceiling is a particularly interesting development. So we start with drawings. And when I first saw these drawings, these very simple schematic drawings, I realized something very interesting. And that was that they look really simple until you try to draw one. These are much harder to generate than they look, because if you notice, there's a fair amount of information here, but there's also implications for what happens in 3 dimensions, the way the walls are built and braced, our decision to build coupled walls. And in this particular case, the existing structure is shown in blue. We built this sort of tan structure, and the tan structure actually comes into the room. So the front of the control room would have better sight lines. We also did this because we wanted to limit how far back we went for cost and logistical reasons. This is the rustic cabin. It was part of an old camp. We updated the windows on this side, and this is a window into the lobby area. This is a side window. This is mixed left. This is the new structure. This is the existing structure, and you can see how the two A-frames overlap. So let's take a look at the simplest aspect of this. What shape is our control room? It's a simple question to ask, but it's a hard question to answer. In this case, the front wall is made up of 3 sections, each with a window. In our case, the windows tilt upward so that any energy incident to the window will go up into the ceiling where we have lots of treatment. So these are 3 windows in the front and the symmetric part. The side walls splay. They're about 7 degrees off of orthogonal, which doesn't sound like much, but it turns out that as you move back 15 or 20 feet, you actually have to allow a fair amount of space. The other thing is that because this is an A-frame, the sidewalls can only go up so high at the sides. So that's your limiting factor, and we had to build a much higher A-frame than you might expect because the sidewalls don't want to hit the ceiling. This is where all the exterior windows are. 3 interior windows. There are also interior windows to the ISO booth in the doors. I didn't list those. But getting the windows in this is an interesting challenge because you want to balance sightline and complexity of construction. I mentioned in section that this room has a side window on mixed left and a window in the back of the room. And if you look, our beam, which is sized per plan, this is the inset, if you will. This would come down, and the footer for the existing facility was right here. You can see that the roof comes down, they overlap, and we put a splayed ceiling as well. So, we have a splayed ceiling, which is hinted upward, and there's a base trap right here. And we had to flatten out the ceiling here because we wanted to keep the angle, and look how high the A had to be to let the sidewalls meet this height. So the limiting factor for the height of this room is the angle of the A-frame of the building. Right? Here are pictures at different parts of construction of the rear wall, and you can see this was built out of wood. Most of our rooms are built out of metal these days, metal studs, but in this case, the wood studs were preferred and allowed. We have an isolated ceiling that's supported by the side walls, and we have beams and joist holders. I'm standing in the existing structure looking into the control room. The front wall was built last. Here you can see the window and the entry into the control room, and this is the same window fitted out, and you can see how it slants backward. There's a soffit. This dark color is a acoustical soffit at the back of the room, which holds both diffusion on the front face and lots and lots and lots of absorption. Here you can see the base trap. The base trap comes up about, it's about 3 feet up, and we have 3 layers of chipboard on the ceiling for acoustic isolation, which you wouldn't think would be such a big deal, but in fact it is a huge deal. And the reason for that is that the weight of the chipboard and the cost of doing 3 layers, if you can avoid it, is a good thing to avoid. But in this case, the area is so quiet that people even a half mile away will hear it if you just didn't have any isolation. So we had to do a fully isolated control room, and we also wanted to isolate it completely from the live room for dual use.
We have few questions already. If you if
Okay,
you'd like to answer.
sure.
Simon asked, the A-frame above the mixed room is purely a design thing, or is there any function to the space above it?
Say it again.
The A-frame above the mixed room is purely a design thing, or is there any function to the space above it? He asked that question a bit of time ago before you were presenting another slide, I guess.
Oh, this.
Maybe the earlier one, where you were discussing the A-frames.
Let's see what we have here.
Yeah, I was just busy answering all the questions related to this joining, so I just looked at it right now.
This is the A-frame. The space above here is only needed so that if, I wish I had a better picture of it. If you look at the buildings, they're both A-frames. This is an A-frame in one direction, and this is actually an A-frame in the other. This one is shallower because it has a different rating. But the point is that at the side walls of the control room have to be high enough so that we can have a ceiling across. It's if we're going to do it isolated and not hang it from a ceiling, but support it from the side walls, it needs to be pretty straight. We have done jogs and things. You'll see that in future slides, but that space is only needed to get the width of the control room. And it's a big expense. Right. This base trap, we're going to see 2 other rooms where the base, did that answer the question, I hope?
Yeah, absolutely.
Right.
And
Great.
we have a couple more questions as well.
Go ahead.
Yeah, Jonathan just said if we can keep the questions to the end, I think it spoils the flow. Yeah, that makes sense too. What do you say, Sam? Do you want to take questions in between, or do you want to
If
keep
you
it to
think
the
it's
end?
urgent, but Paul, if you think it's urgent, ask. If not, we'll go just keep going. All right.
Sure.
Here
I
is
guess.
right. Here is the base trap. We used duct liner in this space because we're going to dump air in here and let it drop down at very low velocity. But behind this are some base traps, diaphragmatic absorbers that we put on the sidewalls. And this has actually got 4 inches of fiberglass behind it. So this is 6 inches of tonally balanced fiberglass, and then it's covered in duct liner. So there's a tremendous amount of absorption. And then when the cover goes on here, the air ducts come out the bottom and it's fabric, so it's open. You'll see that in the next picture. Here you can see some acoustical soffits at the front of the room, and these are going back. This surface at the bottom always stays at the same height, but when you take photos at different angles, it always looks angled. This is the This is the base trap. Again, when we were framing, and you can see the 3 sections of the front wall symmetric, and the ceiling slope is continuous. This slope up at about 8 degrees upward. And the idea is that sound bouncing will be directed towards the rear wall and into a large diffuser. This shows you how we're framing out, and this depth of this 2x4 is for the 4 inches of fiberglass in front of the materials, and then all the chipboard, of course, gets completely isolated. You can see it again here as we look at a different view, and you can see the different types of insulation going in different locations. So why splay the walls? This is a big topic on all the chat boards. Why should you have a rectangular room or not? I didn't see if I can't see the list of attendees, but my friend Christian Carvin and I, who met online talking about acoustics and ended up going to NAMM together to present some work that he did in modeling non orthogonal, non-rectangular rooms. And when you talk to people, they talk about rooms that are non-environmental, or say things like, if you can't predict it easily, why should we use it if we don't know exactly what's going to happen? And I think that's kind of a loaded question, because once you put furniture in a room, you don't know what's going to happen anyway. Things really change a lot with desks and racks and so forth. I think that by coming up with room shapes that as naturally as possible aid you in stopping reflections, where this reflection, if this was a straight wall, would be from here back to the mix as opposed to past the mix. If you look at the other side, you can see that the mix position's getting direct sound, and these aren't obviously drawn perfectly, but if you're going angle in, angle out, you can get hit into a large diffuser, which goes fairly low in frequency. Typically, we run between 7 and 9 inches. Another thing is that splayed walls help you with off-axis energy. Notice that this speaker is, when it fires off-axis from, let's say, 300 hertz and below, the waves are quite big, and they're still directed backward and away from the mix. That doesn't mean that you're not going to get any energy, but most of the energy goes that way. And so for this room, we put a lot of elements to create the sound we want. We decided to do it a box-in-box design. We decided to splay the walls, again, at about 7 degrees. We decided to splay the ceiling. We also decided that in our box-in-box design, we would pick a ceiling that is suspended from the sidewalls. And the reason we did that is spring hangers are very expensive and very hard to install properly. People hang them in the wrong locations. The springs get too compressed or not compressed enough based on where the springs are. So typically you need a set of springs around the outside, which have a lesser load than the ones in the middle, because the sidewalls are picking up some of the weight of the jip as it reaches the sidewalls. We splay our glass walls to direct sound upward. We just looked at that. We put bass traps above monitors. We designed now to put bass absorbers below the monitors on the floor in front of the wall. Lots of diffusers on mix right and left as whenever possible, and at the rear of the room, and sometimes above the mix position, depending on the type of monitoring. Absorptive soffits around the room, asymmetric rear corners. I know someone's about to have a fit somewhere because people always yell at me about this. We've been doing this for like 30 some years. The first one we ever did was the old air show mastering in Boulder, Colorado. And we did it again 25 years later for the new air show mastering in Boulder, Colorado. Symmetric front wall and very low noise HVAC. We designed for NC15 for most recording studios. The reason is, gives us a little bit of a safety factor. We're happy with things under NC20. Also, the data you get from people is hard, but the expense of designing for NC10 or NC5 is so much money to get ducts that long, silencers that long, units that have special fans and doubled walls. And it really has a huge cost to get low. And we'll talk about that in a second. All right, Paul, any questions before we move on to the next room?
Let me see. We have David asking, please discuss the floor. Is it one slab or is it floating?
This is a built-up slab that's it's a built-up slab that's floating. I'll show you the floors in a second.
Then we have Michael asking if it looks like the 3 front windows are slightly different sizes.
Yes.
Is it so?
The middle one is larger.
And then we have Steve asking, how did you decouple the flow between rooms? That's again, you'll be explaining later. What type of
No,
membrane
no,
material
no.
you
Hang
use on
on,
the
hang on,
walls?
hang on. We're here. I can show you.
Oh, all right.
This is actually interesting. I don't know if this is going to work so well or not. Okay, so I'm going to zoom in and zoom out. The existing building is here. This is the edge of the existing building. Nothing on this side of the imaginary line across here, right? Nothing over here touches anything over here. They're disconnected buildings. There's an inch of neoprene, believe, to guard it. If you look, you can see that the isolated floor is right here. And what it is, it's a built-up floor that has this has 1 inch, no, 5/8 inch SR board, um, plywood, hardy board, plywood, and then a little finish trim layer, and there's a finish layer. So it's about, without the finish layer, it's 2 3/8, 2 5/8 wide. And here you can see the ceiling joists are supported by the high walls. The floor in this room never, sorry about that. The floor in this room, in the control room, never touches. It ends here, and these walls sit on our isolated floor. So it's the same floor as here, put down in this room because they're completely deconstructed, deconnected. And I think that's it. That there's a floor here, a floor here. They never touch. The walls sit on them. They never touch. The only place that these walls are connected in any way to these walls would be through a resilient sway brace that's required by structural loading. There are only, I think, 12 or 15 of them along this whole front wall and this wall as well. All right. That was a good question.
Do you want to see more of them? Or
Sure. You want another question? Sure.
yep, we have Sam asking, what type of membrane material did you use on the walls?
What kind of what?
Membrane material.
Oh, I buy the bass traps from Richard Lenz at Real Acoustics. I love the bass trap, the bass mods, 4848, and for different projects, you'll see we get them in different sizes. They're able to model them well enough to they're able to model these well enough to really predict how they're going to behave very accurately. And so we pick the frequencies we want, and we pick the dimensions. And the folks at Real Acoustics, I should mention Braden, that's Richard's son, who's running the place these days, can do some pretty wonderful things. Okay, one more. We're going to move on to air show mastering. All right, let's move on to air show mastering.
Cool.
Okay. This is one of my favorite mastering rooms in the whole world. I love this room, and I love these monitors. These are the original Dunleavys, and you'll see Duntex in a sister room to this. This is an acoustical soffit again. There's absorption behind. These have thin membranes, and this material behind here is the acoustically balanced fiberglass that has a uniform absorption coefficient because it's 2 layers with a membrane in between them. Dave Glasser runs this room. He has wonderful ears. He's a great mastering engineer and someone I love and respect. And he was the first person who let me build asymmetric corners in their room. You'll notice that there is staggered flutter X on the side walls. We were the first people to be staggering flutter X as by itself, or at least that Richard knows about, and other companies have told us. But we stagger them like this because it gives you better better diffusion. They only go down to about 800 or 1K, somewhere in there. And if you stagger them, you go down another octave, which is just great. This is a drawing that I did for Dave Glasser when I stayed up all night at the Telluride Bluegrass Festival. Very sophisticated drawing. But it was an idea to build a bass trap. I guess I should have done this first because this was before we did the other bass traps. We decided to build a bass trap with a hard ceiling and the opening at the back. And the reason we did it that way was because of these, the actual beams were very deep and big and caused all sorts of problems trying to get up here. So we chose to do it this way. And again, this wall and this surface have some low frequency absorbers on them. I don't like the idea of hanging membrane absorbers downward. It seems to put too much pressure on the material. So we don't do that. This evolved into real architectural drawings. This is a reflected ceiling plan, and you can see the consoles here, the splayed walls again. You can see the beautiful asymmetric rear corners, which we'll talk about in a little bit. There's the room shape. There's the asymmetric rear corners. There's a large diffuser that sits on this center line. Notice that the use of asymmetric corners means your rear wall segment is asymmetric, but we always place the diffuser not in the center of this segment, but on the center line. That's the area of opening to the ceiling above. That's this area in plan or in reflected ceiling plan. That's the opening when you look at it, and you can really see the difference in the sidewalls and how it makes this. These are on center line, so the center line of the room is somewhere here, and you'll notice that the amount of room to the right and the amount of room to the left is off. And what's amazing about this is that once we put all the diffusers up and all the soffits up, almost no one notices that the room is asymmetric. Those show you the two asymmetric corners. Right? I just want to say again that this room, and I'll go back to it, without doubt, is one of the best imaging rooms I've worked on or worked in or heard. You sit here and shut your eyes and you point to the musician in the sound field. It's actually incredible. I brought some very, very good engineers who thought I was joking around and had a center channel on. So I had to turn the amp off and disconnect the center channel. They had to walk up and touch the drivers to believe that the imaging was that strong. It was really a really, really fun, long listening day. Really good. Okay. The sister room to Dave's room, and the story is that Dave had a complex like this where he had 7 or 8 different rooms, and he decided to shut it down to build one room up in the mountains, about a 8-second bicycle ride from his house to his studio. And we built that room that you just saw. And here is the sister room to that, which was called Air Show East, or now it is Tonal Park in Tacoma Park, Maryland. And we had a fun architect, Vitillo Architects, and a really fun general contractor, and everyone really worked hard. This is version 26 of the layouts that I did. There's a control room, a live tracking room. This room is was added years later, so this was a hard wall, a demising wall to another venue, another tenant. And then we have main mastering room, closet. You can never have enough storage space in the studio. We do an equipment room, and there are glass doors here so that when you work on it, you can get to the front of the back and use the hallway as part of your equipment room space. This works when you don't have big bands in this area. So this would be, people would come enter here. There's an office, a kitchen, some couches. You walk down this hall, you either walk straight to the restroom and our electrical path, and then you can go into the control room here or the tracking room there. And these are the three main control rooms, all with asymmetric rear walls. This room is Mastering A. It's the most important room, and it presented a unique challenge, a really, really hard one. And that was, there's a column right here, and there's a sort of little bit of a column right here. This column is obviously embedded in the wall. I didn't highlight it, but you guys all know that, what it looks like. And when you look at this, you'll notice that this column does not go orthogonally across the room. And I think it's really interesting because if you look at the way we built the double walls, we go around the column. So the column is encased between our outer wall and our inner wall. I guess you can see that here maybe a little bit better, right? So this orange or whatever color is the inner wall, and this is the outer wall. So the question was, could we put a bass trap up here, and what would happen if we had a weird angled wall? And I thought it'll just be less modal. Let's try it. And we came up with this section. The yellow is our box and box, the layout of our box and box. This is our soft acoustical soffit. Notice that the hard chipboard isolation ceiling drops down among this beam. There's cyan, this hatched, this is all fabric. So you could put your finger through the cyan line. Similarly, mostly fabric over here. We did bring in some air ductwork into this base trap. And again, lots and lots of layers of different density of fiberglass. This is just in there. The position isn't exactly fixed at this point. I was still drawing. Notice this dotted line. This dotted line is what happens if you stand here and look at this. You see a certain amount of beam and you see more beam, right? It's, if you stand here and you were to look up, you'd see the whole beam. So that's what that indicates. And what did we do about that? Well, we built two on this side, exactly the same covering that we put on mixed left. These are the done techs. Notice all three are the same size when they go to surround. And the red fabric with the large diffuser, HVAC diffuser up here, that's the base trap above the monitors. This is again 4 inches of different high density and low density absorption, diffusion on the sidewalls, a large diffuser. This is actually my diffuser from my room in my control room in New York. This is set up for stereo or 5.1. The acoustical soffit that we saw, again, allows ductwork to be used over here. And you can see the asymmetry more clearly in this room because I made it a little bit bigger here. You can see the asymmetric rear corners. And I took pictures looking left and right from the same spot and pretty much got that. So you can sort of get the feel for how the asymmetric corners hide themselves. So to show you how strongly I feel about, I wanted to show one other thing here, I'm sorry. These rooms have no glass at the front. And I'm convinced that if you can put no glass at the front, it's better. I really believe it. I think that glass tilting upward is really important. So I took this idea of building rooms with glass tilting upward. And when Jazz at Lincoln Center invited me to be one of the lead designers for their home at Columbus Circle in New York City, this is the informal room. There's a full concert venue to the rear here that holds 1,300 people. This is a 600-700 person room, depending on the seating configuration. but the main thing to see is the slant of the glass wall. This is 74 feet by 56 feet tall. But Paul, if you want to translate that to metrics for people, that'd be great. But it's a 54-foot tall wall, and you can just barely see it. But can you see the skyline diffusers here? We needed a diffuser that was class run, so there are 1, 2, 3, and then a fourth line of diffusers. They're 50 feet wide, and each one is 50 feet across the room and 4 feet this way. Above them, we sprayed absorption on the ceiling, so all the sound bouncing off this wall, a lot of it is hitting the diffusers to create more diffusion in the room, and that's how the diffusion works. And there would be 4 of these lines, one there, one there. These walls are fabric, and behind them is a ton of absorption and hard surfaces and diffusers, similar with this back wall. And this stage is long gone. They now use just a standard portable stage because this was too restrictive. Let's see, anything out. This room has a Meyer system now. When it opened, we opened with a JBL system, and it overlooks Central Park, and that's 59th Street in New York City. And it's just super cool to experience a band here overlooking this during the day or at night. It's an amazing way to spend a couple of hours. The music takes on a new meaning. It's really fun. Any questions about those rooms or anything that people are thinking about?
Yeah, we have some interesting questions. Let me find out some of the best ones. Samuel asked, is there no resonance problem with the box-in-box design with the airspace around the inside box? That's a good one.
Say it again.
Is there no resonance problem with the box-in-a-box design with the airspace around the inside box?
Oh, that's a great question. Yeah. I'm going to go back to my little box-in-box thing here. No, the more airspace you have, the better. That's actually a funny thing. If you think about what this looks like when you build it, right? This is an isolated ceiling, and this ceiling is going in and out of the walls across. So it's held up by structure, and this white area would be airspace, right? We have a minimum airspace because we try to go as high as we can. But if you're thinking about this, this is typically a 6-inch stud plus at least an inch of airspace, plus 3 layers of gyp here. So this is quite thick, and the insulation that's sitting on top of this is facing upward. So we use 6 inches of insulation, and we usually try to extend to the underside surface of whatever's next to us. So when we build it so this is a dead space. It works out as part of our isolation scheme. Anything that gets through, most of it gets absorbed in the existing structure. So no, we haven't had any problem with airspace. We consider it we want as little of it as we can, but we also want to make sure that we get enough separation so that the places that are really close are very few.
Yeah, I just like to add that I just understand where the question from Samuel comes from. Like, I'm sure if you've seen many studios designed with not a proper design backing it, like a 5/8 layer of drywall inside and a 5/8 5/8 of drywall outside.
No. Even if I could put drywall in there, which would be incredibly difficult and expensive to build, I'm going to go back to this, right? If I could put drywall on the top of this, I wouldn't want to. And the reason I wouldn't want to is you're creating 2 cavities instead of 1. The bigger the cavity, the more complex the cavity in geometry, the better.
Mm-hmm.
Yeah, like if you could build a wall and then build another wall and then build another wall, right? if you have 3 walls, would you want to build it that way or not? And I'll show you some examples later where I've used triple walls, but triple walls have an interesting thing. What we do with a triple wall is we use 2 air spaces. So there's a total of 4 layers of gyp, not 6. And that's very important for performance.
Yeah, it has to be a resilient assembly.
In that case, it's completely not touching. It's completely isolated. I'll pull up a picture of it later if you like. Would you like one more question?
Yeah, let me just sort it through.
While you're doing that, I'm going to say, I use Dave Glasser's studio as an example. So if you guys are in Boulder or in Colorado, you should all stop by and visit. And you should call him like 1, 2, 3 in the morning the night before to ask if he can see you the next day. He'll appreciate that.
Yeah, absolutely.
You got a question for us?
Yep, Eric once asked, when you were discussing the asymmetrical corners, what is the benefit of asymmetrical back wall? What problem does it solve that a straight back wall doesn't?
I'm gonna ask you to hang on for about 10 minutes and then we're gonna look at it. The quick answer is it helps the mid-bass response from about 65 hertz or so to about 90, 100 hertz. It smooths out the response in the room. That's his work that Christian Carver did, and I want to make sure it's properly credited. And we'll show some of his slides briefly to show you exactly what I mean by that. I wanted to show all the different methods we use. So this is a room. This room has wooden slats, and you can see the wooden slats here on the underside of the balcony. It has wooden slats wherever it's lit up here. You can kind of see that they're wooden slats. Wooden slats here behind the lowered level at the back of the stage are acoustical diffusers like you'd find in a studio, and in front of them hang banners that you can pull down. So when it's an acoustical performance and not an electric performance, you pull the banners up and then you pull the banners down. Originally, we wanted this cloud to be operable, but it's not. By the way, building a cloud that's free hanging like this in San Francisco is incredibly difficult because of the earthquake restrictions. You have to have steel tying everything together, which we'll talk about. This room has a little bit of variable acoustics behind there. It has variable configurations where seats in front of this wall and these walls are retractable. So you can have a flat floor for dancing. You can have extended seating, or you can have fully seating. There's 1 row of seats behind the stage. That was an interesting discussion. There's some diffusion on behind this, which was one of the 2 video screens. There's one that can drop out of this slot. This is a Meyer Mina system, a 5-element cardioid subwoofer array, and some side fills from the JM series of loudspeakers. This picture is a little misleading. It's not that steep. Notice that this is an acoustically transparent ceiling. It's just wooden slats. And the reason of that is we want the room to have a larger cubic sound of cubic volume more than it appears. We want it to appear intimate, and we want the room to have some bloom to it. There's a mixed position, and you'll notice that on stage right and downstage center, we have balcony seating, but there's no balcony seating on stage left, right? So the other thing is the balconies are very shallow, so unless you're standing, you don't feel like you're under a balcony. Putting people under balconies acoustically and visually separates them from the performance. If you can't always avoid it. This is the sound system and a fully diffusive canopy. There are 5 subwoofers up here. You'll notice that if you count them 1, 2, 3, 4, and 5, these 2 are facing backwards. These 3 are facing forwards. a very large number of minas. That's the maximum you can put on a fly bar, and our side fills. So there's our sound system. And while I like to keep the subwoofers under the stage, they do a lot of different work in this venue, of all different types of shows, and they wanted the stage to be very low. So we fought for every inch of stage height, so we could get sound up and up here. And then this is completely diffusive behind the white fabric. This is the team. This gentleman is Randall Klein. He is an amazing visionary. He founded the SF Jazz program, and this building was his dream. This is a great engineer and trombonist, Jeff Cressman. And this is the great Len Arbach. Len is one of he just retired this last year, but he's a Taekwondo master and one of the most prominent theater designers in the world. He's a wonderful guy. So there are great people on these projects. You can start to see that above the fall ceiling, we have a figure-8 catwalk where you can walk around and see what's going on. And I wanted you to see what these things look like when they're under construction a bit. This area has both HVAC ducts and attachments for the chairs. This is the canopy. That's me. There's a shot from looking down onto the canopy, and you can see the back of diffusers. These are from RPG, and we rotated them 90 degrees because back in these days, 15 years ago, getting a mid-frequency two-dimensional diffuser was really, really hard. So we made them by staggering them, and we left some holes open to let sound through and up, again, to encourage some late reverberance. You can start to see the steel and the amount of steel that's in this thing. This is a room where all of these techniques are also used. One of the things that happens in rooms is that, and I knew I wanted to make a slide I forgot to make. There are basically three configurations for concert halls. There's the shoebox, there's the fan shape, and there's the reverse fan shape. So in the reverse fan shape, you have angles that are pushing sound back in towards the audience. And while that's used mostly for classical halls, it also shows up in theaters. Materials and shaping, these balcony fronts, notice how they step back. So these people, it's quite a good gap between them to keep the amount of space as big as possible so people don't feel like they're in a balcony. And these people, if they look up, will see not the underside of this, but up. You can see the steel up here. We put a huge amount of steel in this room. This wall is made out of MDF, and I use these black pieces to hide the seams. And you can see that we have some ductwork in there for even airflow. This is in Las Vegas. It's the pearl at the palms. This is actually a photograph that someone took and just, I guess, smoothed it all out because it looks like a picture. But I wanted to show you that this area where these white lights are is a large bass trap. And this was 20 years ago, and no one made a bass trap that was this big. So what I did was I made some membranes and I glued them between duct liner frames, and we covered it all with duct liner. So it's like 8 or 10 inches with a membrane in the middle, and it sucks, below 60 hertz right out of this area. It gives you a really clean sound, but most importantly, it eliminated that mid-low frequency reflection that happens when you keep the farthest seat from the stage to be 80 feet. Another interesting thing about this project that was so crazy was this was the ground. If you walked outside, you could walk in and out and jump down. The point is we had to dig this all out, and that turned out to be a huge problem. These pieces are perforated metal with different densities of fiberglass on the balcony front They curve in plan, and you can really see how they scallop in section. I just love this picture. I don't know why. Just the way the light's coming in when everyone's working, and it's just, I get thrilled when I'm walking around the site like this. I remember taking this picture, and I think Rob Scoville was with me. That what they did was they built a ramp so you could get up and down onto the stage, and they built another ramp to get materials in from outside. And here you can really see the perforated metal, the slatted wood. These openings are really interesting. I hate sitting under balcony spaces because it always sounds like this. And when it doesn't sound like this, I'm getting a delay speaker that's way too loud. I want to shut my eyes when I'm sitting under a balcony and point at the stage, not at the delay speaker. I think that's a big mistake that people make. So you want to get this opening as big as possible, and you want to get as few people under there as possible, which means that you're pulling the room in and out at the same time. It's a really difficult design challenge that often comes down to sightline studies and inches. This was a great night. I don't know how many people know Dave Natali. Dave is a really idiosyncratic, has a reputation to be super cranky. So these guys over here in the picture are sitting there, and I'm actually behind Dave. I was sitting on the end because Dave doesn't like having anyone around the console. And the guy could not have been nicer to me. He's like, hey, you want to come sit next to me? And I'm like, sure. I love that idea. And let me tell you, it was the best sounding show I've ever heard in this venue, and one of the best sounding shows I've ever heard. It was Jeff Beck, and it was about 2.5, 3 months before he passed away. But Dave, who mixes some of the best rock bands, does it on a console from the 1980s. He does it on an old Yamaha PM 2000 that he swears has not been rigged up. It's just a great console, and he likes the sound. He said it was recapped, but it was really fun. This is one of the bands that has a residency there and likes to do fire stuff. And oh, the difference between these two gigs is this was a seated floor show, and this one was a standing room only. And here's an interesting thought for you. If your room is going to do both, you've got to make the sight lines work for both. And more importantly, you got to think about where those chairs are going to go. So chairs take up a lot of storage space, particularly for, 800 and some chairs. So you really have to know where they're going to put them, because the operating cost of moving chairs off site and on site for shows is a problem. This is another room where our architectural methods meet our design goals. And this is in Nashville, it's a Brooklyn Bowl. There's a bowling alley over here. There's a bowling alley up in the balcony, and the bowling alleys are at stage height. You can see the walk down from there. And so in theory, you could walk to that line bowling alley. And then there's an area behind the bowling alley here where people who are bowling can stand on the rail and watch the show. Interesting enough, you can't hear the bowling alley on stage. I don't know if that would work with an acoustic band that wasn't amplified, but it's really hard to hear because we've really isolated that slab from our slab. We've isolated any structure there from the structure over here, and we've done a ton of absorptive treatment above the bowling alleys. This is a trick I hate to give away. This is not the final curtain. The final curtain is a much heavier 22-ounce velour, but they delivered this until it could be ready. This was as COVID was starting. This was getting ready to open, and you couldn't get everything you needed right away. These are base mod 96, so they're 8 feet tall and 4 feet wide. They're 96 48s, and they're tuned to different frequencies. The lowest one, I believe, is 48 hertz, and the highest one is 65 hertz. And there are a couple in between, and they run over to the sidewalls over here as well. And it's one long line, and it cleans up the stage dramatically. It's unbelievable how great it makes the stage sound, because it takes all the low end, and even though we have cardioid subwoofers for singer-songwriters, which is huge in Nashville, and for bands with intricate finger work, they get swamped. They can't hear each other. They want their monitors louder, which it's a cycle. And even in-ear monitors don't solve that cycle. People just turning themselves up in every place to cut through the low end on stage. So I think this is a great idea. I have a couple more quick ones for you that this one's not as quick, but it's a fun room. This is in Boulder, Colorado, and this is E-Town Hall. I took an old church, and we were standing in the church in the basement, and I grabbed the column and shook it, and it was loose, and we all ran out of the building. And we had to take the first floor out. So expect the unexpected, and we created new structure so we could keep these stone walls and the existing ceiling, which we scraped all the plaster off of these and replaced the ones that were rotten. And as you can see, a lot of this looks like it was over 100 years old, because it was. And out of the floorboards, we made a diffuser, which I rotated. This was a Prime 13 diffuser, which is the same as these FlutterX strips at the mixed position, which has absorption over here and some diffusion behind it. This is a historic window. It has ever so slightly tilted upward. And you can see the tilt of the glass in the control room below. This is the supply air, and then it dumps the air low, slowly, like 250 feet a minute. It's nearly silent, and you can see the upgraded controllers and different sized windows in the walls, some additional absorption, an alcove for equipment with its own cooling, some diffusion on the sidewalls. And these ceiling beams are being held up by the sidewalls. And we built a pop-up in it as well, which never braces off of the structure above. So none of this steel ever touches anything above it. And here you can see what the studio live room looks like. Someone donated these Skyline diffusers. I'm not a big fan of them, but when they donated them, and for those of you who would like to see go to etown.org. I was on their board of directors for a couple years. I love these people. I love what they do. I'm going to show you the beginning of a time-lapse video. Let me know if this works. I don't know if it's going to pass, audio to you guys.
Sam, I think it's coming from your mic, not from your system directly.
You want me to shut my mic off or not?
Try doing that once.
Should I do that?
I think that the audio is coming from your mic, not directly from your system. Do you see any option of sharing system sound?
Yeah, I don't really. Yeah. There's the floor that's the floor that was existing, and these are the columns that were loose. So the whole thing had no structural integrity at all. But look at these old crazy curved beams. And then someone tried to take this old curved beam and support it this way. I mean, this was just not safe. So and it was a big challenge for the project, because it added $100,000 to the cost. Here goes the acoustic floor. Whoa, no, no, no. Oh no, what did I do? I'm going to just grab that and try and show you what that is, because that was a moment I want. Right. So this is the acoustical floor going down, and you'll see that here, here are the kinetics. This is the rim system. These are 2-inch compressed fiberglass pucks that come in the fiberglass. So the green pucks sit at these cutouts, and this ensures that you can't get it wrong, because you can do it either way, but they can't be on their side, which is a way people screw it up all the time. So we sanded the subfloor, got it all nailed down, and so that it was relatively smooth and locked in place. Then we laid down the kip pads, then the plywood. This is the cardboard honeycomb called SR board, which is a really cool product. It gives us a discontinuity layer. So there's 2 inches plus 3/4 of an inch plywood plus 5/8 of an inch of SR board, then 3/4 of an inch of plywood again. I'm sorry, then hardy backer board, then plywood again. So that's about 6¼ inches thick. Look, I get show my face. This is Jim Walker, our architect, a great guy, one of our contractors, and this is the owner or founder of E-Town, my friend Nick Forrester. And if I tell you that 3 seconds represents about 2 years of my life, is there anything else we need to see? Oh, this is fun. When they sprayed the K13 on the ceiling. Oh, I missed it, sorry. It gets all foggy. And this is what it looks like when it's opening. Okay. One more project to make this point. This is a jazz room in St. Louis. This is the Jazz at Lincoln Center Orchestra decided to open it, so they could see if I did a good job or not. There's diffusers behind here. There are membrane absorbers behind there and diffusers. And these are the 2-dimensional diffusers, and these are the 1-dimensional sort of pre-good panels. And we put them in there with an acoustically transparent fabric above the band. Any questions on that section? How are we doing for time? We good, Paul?
We have some good questions on the older sections, though, not on this one right now. Do you want to attend those older ones?
Yeah, let's take 2 questions, and then we'll bang through some other stuff and move on.
Sure. Mark asked, what was it like working with the architect on a project like this in Vegas? I forgot which product.
Yeah, that was the Pearl. It was great. He's a friend. He's an incredibly good guy, and I recommended that they hired him. I was brought on board before the architect, the final architect, was engaged. And what I did the same thing that Russell Johnson used to do, which was come up with a concept, sell the owner on it, and then work with the architect to flush out the details. But that was Bill Murray of Pfeiffer Associates, who's world-class venue architect. Great guy, really talented guy.
And we have David asking,
Yeah.
for its question answer. Yeah. Is there an advantage to hang a subwoofer instead of having it below the stage?
Yes. When your stage is so low that you can't fit it and the stage is going to be reconfigured several times a week, I would rather have subwoofers low. And in that case, we used beam steering to steer them downward, which I could probably pull up at some point. The big advantage of having them up is they're up and out of the way, and they're used for all the shows. And if they need to put subs on stage for a hip hop show, we bought them some extra powered subs that are cardioid that they can run out to the edge of the stage, right and left or center. when you have 30 different orchestra configurations or band configurations or flat floor or seated floor or stage floor or risers on the stage every week, getting the subs up and out of the way really helps. It's not a fixed stage there. Lots and lots and lots of stage. The stage is actually fixed, but they add or subtract to it regularly. So it's very hard to get them low. I can do this here. Just to refresh your mind about that real quick. You can see that we actually have room to put a sub there, but not a big sub. And when you look at the amount of power that they want, this works really well. And the other thing is, because it's a cardioid, when you point it down, you can decide how much low end needs to go where. And it's really incredibly uniform and very, very, very. Now I got to find out where I was. Great. So we're going back to where we started, right? Acoustical designers, right? We use measurement to get us from perception, what we hear and what we want to hear, to architecture. And what I've tried to do is show you over a bunch of projects, many of the solutions that we've used. I didn't talk much about ductwork and HVAC and isolation, but you got the idea of isolated ceilings and isolated walls, etc. What architectural methods do you have to impact rooms? You can change the size and shape, right? For control room, shaping is important. I think shaping shows up whether you have a balcony on house left or not, for example. Construction details of walls, ceilings, and floors. Are they resonant? Are they 3-panel, 2-panel, 1-panel? How are they built? The selection and distribution of finishes, I should say, also the details of how the finishes are attached and ambient and isolation noise, right? Problems. The only 3 methods we have in acoustics that are architectural are we can absorb sound, we can redirect sound, and we can diffuse sound. That's it. Everything we do is either 1, 2, or 3, or a combination of those. I love doing mid-high frequency diffusion with low frequency absorption behind it. I love slanting and splaying walls. So if measurement is our goal, is our tool to help us understand what the architecture sounds like and how to impact the architecture, let's look at, you can measure ambient noise with a real-time analyzer. You can use NC, blah, blah, blah. You can do transmission loss. You can do reverberation time. You can do direct to reverberant level, which I think is super important. Early to late energy ratios and frequency response and spatial distribution of sound. So these are all types of things that you can look at and determine quantitative values that you can use to evaluate what you think is good, bad, and what you need to change to improve it. So real quick, people used to take pink noise, play it through a system. They'd have a microphone. The microphone would play the pink noise. It would be bumpy. They'd pull this up. They'd push that down. They'd get it to look flatter. They'd listen to it. It sounded crappy. Why didn't this work? Why didn't this work? What about this process is fundamentally flawed? And the answer is you don't know what the sound is doing at this microphone. Are there reflections to this microphone? Are the speakers out of polarity? Is the ambient noise? Is someone standing next to this whistling? Right? There's no way to tell that from this graph. So we made the system a little bit more complex. We put a source signal into a mixer, whether it comes from a computer or it's not, it doesn't matter. It can come from the band. It goes out and we just take a sample of the signal going out. We could have just taken that from here and just put it over there, but whatever. That's the reference signal A. B is the output of your DSP processor, and C is your microphone. So if we compare C to A, we get the whole system, including the room. If we do B and A, we get just the response of our processor, if it has delays, if it has equalizers, whatever filters are in there. So we can look at those things very easily. Now, when you compare two signals, what you're looking at is called a transfer function. And the transfer function can be represented and measured lots of ways. I mean, there's a bazillion ways to measure transfer function. But you can represent it in the time domain or the frequency domain. There are other ways to do it as well, but 98% of the time on this planet, they're looking at it at the time or the frequency domain. The transfer function in the time domain is called an impulse response, just so that everyone would be confused. The simple impulse response is the perfect impulse called Dirac deltas function. If you were to represent what this means, some sound left its source at time 0, it arrived at you with this level, and it had every frequency that was in it because this has a perfect frequency response. That represents free field condition, right? Here's one where you're standing there, you hear the same sound, and then sometime delta, you get a spike with a little bit less energy. Now let's just assume that the two are don't have frequency responses. They're just bandpass filters. It just lets the copy of the sound in. If you did this, you can do it on headphones. And as you change delta from parts of a millisecond to 20, 30, 50, 100, 200 milliseconds, the way you perceive this reflection is different. That's a good thing to do for everybody to try it. This graph I made in 2011. I found that out this morning when I found it, or yesterday when I found it. And it was one of the first impulse responses I used to show what SMART was doing. And the direct sound contains lots of information. And here are some reflections. You can see a couple more down here. And this this dip right here, that's the initial delay gap. So the sound goes out, it bounces around a few times, and then the diffusive field starts to build up, a reflection comes, and the diffusive field decays away a bit, and then another reflection comes, then another reflection, and decays. So that's the reverberant decay, that's the noise floor. The impulse response is a self-aware metric in that the quality of your data is a function of the dynamic range of your impulse response. So if your impulse response only has 10 or 15 dB of dynamic range, you either have to open up your time windows more, or you have to do something. All right. Here is how you find the reverberant level. This is broadband. This is the level of the difference between the peak arrival and the direct to reverberant level. I bring this line back, I pick an approximate point, and I say this looks like it's at like, I don't know, 16 dB, and this looks like it's at minus 40 dB. So you'd be like 24 dB of direct to reverberant level in broadband, which is very good. And we'll look at it at different frequencies to sort of get a feel for speech intelligibility. If we want to isolate the direct sound from the loudspeaker, like people used to do to make semi-anechoic measurements, you have a big problem, because when this window is short, right, you don't have any low frequency energy. There's not enough time for low frequencies to be seen. And in a traditional FFT, your data points are very far apart. So you have too many data points up here and not enough down here. So if you open up the window, then you're seeing the direct sound, but you're not isolating it because you have all this room acoustic stuff in it. But now you have nice resolution at low frequencies below 200 hertz, but still excessive resolution at high frequencies. The paradox is resolved by using DSP to open multiple time windows in a single measurement. Short time windows at high frequencies, longer windows at low frequencies, and multi-window time measurements correlate extremely well with human hearing. So if you have an impulse response of a room, instead of taking n data points and trying to analyze it, we take a whole big array from very, very short, typically 1-2 milliseconds, up to 3/4 of a second. And what that looks like, we used to call it the fixed point per octave transfer function. I think I don't know what they call it, 24 points per octave now. So this is also from 2011. Sounds like a long time ago. So this is a difference. So it would be better if we drop this down to line 0. So because the high offset is the difference between the levels of our input and output of our system that we're comparing. So what I do if I have a graph like this and I can't just grab it and pull it down, which you can if it was live, I just draw a horizontal line that I think represents 0 dB in this response, and I see what's above it. And I immediately see 3 problems. I don't remember exactly what control room this was. I know it was a control room because the file that had this says control room measurement, mixed position, both speakers. And you can see that we have what look like modes, very strong modes in this room. There look like there are at least 5, if you want to count that as 6. I generally don't look at modes above 200 hertz very often, so maybe include that. To me, this dip, I would immediately press the phase button so I could see the phase. And what the phase would allow me to do is see that this is 2 arrivals, left and right, canceling each other. So I would move my microphone a touch until that went away, and we could see that easily in the phase response. But reading an impulse response is incredibly important. I would immediately worry about any peak up at 3K just because your ear is so sensitive to it and it's harsh and nasty sounding. I would get rid of that. I would get rid of that. I don't know. I would listen and try to solve this problem. I would look at where the subwoofer was and if I could cut this here and interact it. It doesn't look like there's no subwoofer on in this graph. The ability to measure the transfer function uses this multi-windows, and it lets you see equal resolution at every octave, which is what we have. If you listen to a piano and you just go on each octave, each note is an equal step. Very important concept to understand. Ideally, using these methods will have a better understanding of room acoustics. Systems can be made linear and then subject to artistic issues, input versus output, etc. Before we go any further, this is Christian's part. Do we want to answer some questions?
There's a couple of those. John says, my experience is in large rooms. What is your approach for impulse response and transfer functions in small rooms dominated by modes? For example, do you measure and design just around mic position?
No, that's very interesting. Absolutely not. And funny, what's really funny is that one of my favorite measurements that almost no one makes is the measurement of a, hang on, I'm going to do this. Hey, I can see you guys. Oh, I can't see everyone. But anyway, no, I like to put a microphone on the floor in a corner of the room and play the subwoofer because you can really see the modes. I'm going to repeat that. Put a microphone on the floor in the corner of the room, any corner, and you'll see the modes very, very clearly. And almost no one makes that measurement. I don't know why. What I do is I calculate the modes for any room that we're in, whether they're eigen modes, which are modes that are calculated without source position, or they are, and I look at the different things I can control, like the amount of low frequency absorption, the location of the subs. We tried to do a measurement of a cardioid sub and a standard sub in the same position, but it was sort of confusing. It's been very interesting to think about these transfer functions. What I do know is that you can, we designed, what I said was localized linearity. And the idea is, hang on, if I can get over here. The idea is that you want a transfer function that doesn't have big bumps, that has modes and notes that jump out at you. You want to correlate what you hear. So like at this point at 125 hertz, that's the octave below middle C. I'd look for a note that was really jumping out. Play a piano, go do, 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 dong, do, 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 dong, you know. This is a big boost. This is, a big drop. So you want to find where the response is the smoothest, and then if you need to add more low end, you do. You have to decide. The idea is to make the thing stable and linear. I mean, you guys live in a world now where feedback is pretty rare. We don't hear feedback at concerts anymore because people have more control of their system. They're not firing into mics, and they're getting rid of resonances. With some of this, you can affect the measurement by moving the low frequencies. I see this type of thing a lot when the low frequency drivers are next to each other and people are trying to create a power alley in the control room. And I always put the tweeters on the inside and keep the low frequency drivers as far apart as possible to keep the image correct, but the coupling less. Next question.
There are, I don't think there are any specific ones as of now. There's some generic question that I think would be better enough for the last Q&A session. Or do you want to take one?
Whatever you want. I'll take one. We still got people
Okay.
here. I hope people are having
Yeah.
fun. I hope this is interesting. We've been doing
Yeah,
this for a
people are
long
leaving and
time.
coming in, but we have about 90 people as of now. Yeah, it's still good.
Great.
Okay. So Mark asks, could you please describe how you typically collaborate with the ABL team when developing the acoustical design for a studio or any project?
I just command them to do what I want. No. I've been very lucky to design a bunch of studios with people I really like. One of them is Zoe Thrall. We just did 2 studios in Las Vegas. And what's amazing about those studios is that they're super fun to build. And we debate what the AV system, this morning, I was asked I was asked this morning if I would talk to a client now about how many inputs he really needs in this studio and what he's going to use it for and so forth. So one of the things is you can't really work on AV until you have a chance to really this is over here, somewhere over here. I'm trying to find my pictures of this room and I don't see them anywhere. This has got to be it. Here it is. I found it. No, that's a Japanese chef. Here we go. I've got beautiful pictures. Here's an example where this is a studio that we did, and Zoe designed the systems, but we collaborate on everything. Let me hit share somewhere. The sun has moved and I have, can you see my screen? Paul? Yeah? So,
Yeah, we can. Can you see my
right, this
video,
is,
by the way? I was just using thumbs up reaction, so you know. Can
that's
you see my
great.
video?
Yeah.
All right.
So this is a studio that I really like. It's a small room, asymmetric rear corners again for bass control. There I am. These are the bass mods in the behind the speakers, and they're locked in. They're never moving. We did corner traps to move some ductwork down to provide some air low in this room. This is the wall of hats. It's a really big wall of hats. They sell you a hat. I don't understand why. It's just the way it is over there. But from day one, we talked about how many subwoofers, what kind of monitoring system. In this case, the client picked ATCs, and we auditioned Genelex sub, and they loved it. This is a soundproof windows and doors sliding window slider. It's custom with electric glass. That's the instructions for my angulometer. Here you can see what the live room looks like. Good panels, HR series diffusers on the ceiling, acoustical soffits, splayed walls, the whole bit. This is really cool. This is a, I don't know how, I didn't deal with the money aspect. Oh, that's not it. That staircase kills me. It's got 4K video on it. Anyway, it's a cool staircase. It's pretty rare that you get to see a facility like this. There's Zoe and I think this was early on. There's our electrician, some rappers that came in to hear the place. That's the owner of the store. That's what the store looks like. Fun project. So working with the AV team, almost always we get along well. We really try to figure out what the client wants and how to best use it. Anything else? You got another one, Vipal?
Nope, I guess we should move forward.
All right. So we'll do
Okay,
some
wait. Sorry to interrupt. I just found a good one.
All
Ignacio asks, I made that one. No, I think what is he referring to exactly? Did you make it when the client doesn't have a subwoofer? Ignacio, your question is a bit confusing. Would you mind just typing it down once again? Was there a context to it?
Yeah. This is an interesting one. Simon wrote that he's talking about the time of decay. I'm about to talk about that. You can see that easily in an impulse response measurement, and you can make measurements. I tend to measure right at the sweet spot between the two speakers. Then I measure again on axis with each speaker, and then I go to the sides of the mix position and I look and see if it's different, like if you're moving across. We've been very fortunate using these techniques to create essentially a reflection-free zone and a low frequency buildup free zone at the mix position. And it tends to be fairly wide. It's a function of how big the room is. As the room gets bigger, you have more. I want to talk about Christian's work really quickly for you guys. Here is a model that you can see what I'm sharing, right? Yes? All right, great. So Christian used a finite boundary element method, and we started just said, let's take a square room in 2 dimensions, and you can see the modes of the square room. This is untreated, and these are eigenmodes, which means they're source independent. This is the geometry of the room where it wants to resonate. Once you add a source with directivity, some of those modes get excited more than others. And he was able to look at those modes and come up with a spectral variance from the peak over here to the dips over there. And he found that the spectral variance between 20 and 125 hertz, which is our low frequencies, is 67 dB. And what we were able to do was to look at a rectangular room, and the variance improves about 6 dB. And when you compare the square versus the rectangular, you can see that the rectangular in blue has less overall variance, but neither one of them is particularly good untreated. And when you start splaying the sidewalls, you get a big dip between 60 and 80, but it smooths out and you get better results, and you get 8 dB less spectral variance. And then if you add asymmetric rear corners, you get 13 dB of spectral variance. So we're only looking really from 60 to 100, 125, somewhere in there. And what you can see is that these values, if you have symmetric corners, you get a null right at the mix position. And here you get, with asymmetric corners, you get lesser modes and a more even distribution of energy. And we did this for lots and lots and lots of positions. And so here you can see two-dimensional modes for these. And I want to point out that while people are going around saying it's hard to measure, yeah, you know, Christian worked his ass off to put this software together and make it work, but it's not that hard to do. So the question is, can you do this in 3 dimensions? And we used the room at Tonal Park, which you guys saw some pictures of and the layout of. And we started looking at all the different shapes again, and looking at splayed walls and taking it down and looking at the bass trap. And we could even see the effectiveness of the bass trap, right, with the asymmetrical bass trap. And what we end up with is a set of modes. And this is a 3-dimensional set of, it's walking through all of the different frequencies. So that's 60, 61 and a half, 63, 65, 67, 69. And you can see how the different modes are complicated, but they can be measured and graphed properly. And Christian has nice things to tell you about that. And right. So let's do some final Q&A, and I guess I should keep this open.
Yeah, and by the way, Christian is also in the room, I think. If you guys would, if you think he would like to present along.
Yeah, go let him. Sure, I'm happy. Always.
I think I've allowed the mic, Christian, if you can hear us. You might, you just would be happy to hear you.
All right. Great. Any other questions before we call this a day? It's long. We're 2 hours, man.
All right, so I'll just pen down a few good questions in between the session. So somebody asked, is it possible to remove the room modes with splaying walls?
No. No.
And
Splayed walls are not, they help a little bit for sure, but they don't remove the modes. They damp them. And the difference there is what the gentleman, I think it was Simon, was asking for before, because the question is, now the question is, how long do these modes last, right? And the answer is, we've all seen waterfall plots. I like spectrographs better, where the modes can clearly be seen lasting longer. So what we do is we either use equalization in a live situation where you can equalize out the modes and just put out less energy. They last the same amount of time, but you're putting less energy in. So it integrates over time, and your ear really integrates the low frequencies. So you don't hear repeated drum kicks if they're too fast, right? It just becomes a at low frequencies. It's the high frequencies that differentiate, a kick drum that's being tapped as fast as someone can tap it. The question is, what can you do? You can't really do much unless you're going to do some construction or build a bass trap or add a diaphragmatic absorber of proper frequency. So there's not a lot you can do. We haven't found great modal software, which is why I reached out to Christian, and he's been developing these tools, which are, I think, pretty impressive. I've got half a dozen friends around the world that all use different packages, and no one's completely satisfied that we have a good solution yet. Do you have any spatial stimulation on playing reactive resonators? Do I have any spatial simulations? It turns out that this that we just showed is a spatial simulation of exactly that, because what we were trying to do was find out how this bass trap at the front of this room changed the room with and without that bass trap. And that's one of the questions that we're still moving on. But the answer is it reduces the amount of energy that it's because a lot of the secondary and tertiary, the oblique and the tangential modes, the 2 and 4 and 6 wall modes, get impacted by something this big, or the asymmetric corners, that you're damping and reducing their impact. It doesn't have much on the axial modes, the 2 walls that are parallel, but that's why we splay the walls and the ceiling. Next.
In addition to the previous question about the room modes and splayed walls, if you see the Q&A section right on the above panel bar or whatever it's called, there's a question by Algorithm. He asks, how do you approach design a small room acoustics from few cubic meters to few hundred cubic meter volume, room ratios versus playing? And there's a second part to his question, ideal decay times for control rooms and live rooms.
What was the last part about control rooms and live rooms?
Ideal decay times for control rooms and live rooms. Also, I have a personal addition to this question.
Yes.
Without naming anyone, there's a segment of acousticians who think that splaying walls does not affect on the room modes.
Yeah, I don't care.
What is your
can look. There's two options, right? You can believe it or you cannot believe it. And the answer is, who cares what you believe? Just measure it. Yeah. This data that Christian and I presented shows that when you have a rectangular room that's untreated, it has stronger modes than if you splay the walls. This is a fact. It is an undeniable fact. It has been proven, right? If you have symmetric corners and asymmetric corners and splayed walls, then the splayed walls will in fact give you a better modal distribution and a smaller variance. Now, people will say, I don't believe that for XYZ reason. And that reason better involve some modeling or mathematics or measurements that make sense, right?
Absolutely.
But they almost never do. They're just saying, let's start with the rectangular room because we know we can know what the modes are. Well, there are plenty of people out there looking at modes of asymmetric and non-rectangular rooms. And this is a pretty amazing accomplishment. I think that Christian should be applauded, not
absolutely.
Have I designed a non-acoustical room, no panels, nut corners and ceiling only? No, it seems like a really bad idea. For what purpose would that be? Like to put musicians in, or to record in, or to listen in, or monitor in? So James, no, I have not designed a non-acoustic room. I don't believe that there is a non-acoustic room. I think acoustical rooms, every room, even an anechoic chamber, has I guess an anechoic chamber would be the ultimate non-environment room. So I don't buy into that. And if you don't say the splayed walls change the modes, they do change the reflections. they push the reflections to the back wall. That's a fact.
Mhm.
And if you slant glass upward, it sends sound upward. And you can do that. I mean, I'm trying to show that I like the question about control rooms versus live rooms. I'll get to the small room in a second. The control rooms, right? And the live rooms have a lot of things then similar. You need to isolate them. You need to have low noise. You need to have tonal balance, which I think is the decay rate at high frequencies and low frequencies. And I think I'm going to pull off a cool little thing here, right? If you look at, oh, no, yeah, we in an impulse response? Yes. So here's an impulse response, right? It's just an impulse response from a project that I'm working on, or I thought I was working on, or something. And I'm going to zoom in a little bit for you so you can see that the whole measurement, this is only the relevant part. And we check we have 36, 37 dB of dynamic range in our broadband measurement, and we can put our decay rate measurement. So this room had no treatment, and it was a 1.8 second room. And the direct to reverberant ratio here is about 21 dB, which is really pretty amazing, right? For broadband. So we were either close to the system or it's a very high Q system. And you can see there are a few groups of reflection here. So that tells us something about the distance between that would be about 100 milliseconds. That would be 50 milliseconds to the back wall and then back to where my microphone was. So I was probably 25 feet or something like that in front of the back wall, 30 feet. And you can see that grouping, and we can get some information here. But then you can go and you can look at this in different frequencies. So for example, at 4K, the decay rate is a little different and the reflections are a little stronger than they were broadband. Right, you see that? And we're still getting lots and lots of direct to reverberant ratio because the speakers are fairly high Q. They're directional, right? And as you move down and you go to 500 hertz, you notice that your direct to reverberant ratio is much lower, right? The speakers started to go omnidirectional, or at least less directional, and the reflection is still strong. So this surface, whatever distance this is away from 57 milliseconds to 157 milliseconds, about 100 milliseconds away, that surface has to be pretty big if it's reflecting 500 hertz. And you can look at that at 225, the speaker is exciting the room, but it's exciting the room much faster, and it's a much more spread out sound going through sidewalls. And you can see that. And if we go even lower to 125 hertz, I can bring this up for you. You can see that sound starts rolling around the room. And if you look at these dimensions, you can study them and pull out the dimensions of the room, believe it or not. And you can see that at low frequencies, this room is never going fully reverberant. It's always going to be rolling. And I don't know if we had enough energy at 63 hertz. Yeah, it's just arrival. It's just rolling. There's no control at all in this room. If we look at this room as a spectrograph, if we look at this room at a spectrograph at 63 hertz, we're not going to see much. But we can calculate this, and I think we can zoom in a bit here. And you can see that our low frequencies are much longer than our noise floor. And you can see that here at 125 hertz, we're out at 2 seconds, and at 2K, we're at 172 milliseconds. So you can really see the amount of decay that slants. I can change the well, we could change the color scheme, but the idea is by looking at these, you're able to investigate what's happening at different frequencies and how long things are hanging on. And what I try to do is get a nice smooth thing so that we're at about 40% at 125 hertz, about 140, 1.4 times the average of 1K, 2K, and 500 hertz. And that gives us tonal balance. This is obviously a very loud room. It's not isolated. So that really tells you a lot of what's going on. Any last questions before we go?
Yep, I just found a good one scrolled up. So Elizabeth asked, when designing a control space, do you focus purely on the mix position, or do you consider the listening experience for, say, showing a client or teaching students in that space? And how do you
Ah,
handle that? That's like a mixed position with scout
That's
position question.
it's a really good question, I think.
Mm-hmm.
I really like this question. Here, I'll show you something interesting. So if we go to air show, the only place I really care about is right here because he works alone most of the time. And when clients come in, they sit next to him. No one in the back matters. However, I did, this will answer another question that was earlier too. I think this has some pictures. Those are pics. This is a control room designed for students. Well, it's long. I'll try and dig it up. But what we do is we look at where people are going to be sitting and we look at what the monitoring offers to serve those people. And what we try and do is predict how much sound they're going to get from the room and from the various angles. So when you're building a room that has to fit 24 students, we really went out of our way to, let me just see if I have a picture of this. NYU Clive Davis, it's not. That's a pass that I made for them. That's the console. Well, I can't find it at the moment. I'll find it in a second. But different rooms have different focuses. Someone asked about small rooms. This little production room, the idea was this was for editing and working on small speakers where it wasn't sound critical. And then it became a secondary mix room or a rough mix room. And we added a bunch of low frequency absorption to deal with it. For the room that I showed you in Las Vegas, with this room, oh, did I really lose my room? I'll find it quick. By looking at this room, what we're able to do, this room was tiny, tiny, tiny. I think this room is at the mixed position is 14.6, 8 wide. I mean, that's not a very big room. It's 14 by 20. This is a small room. We're working for the mixed position here, but guests were really important. So we decided to go for non-soffit mounted speakers, mainly because we felt we control the off-axis energy very easily with the bass trap above and the diaphragmatic bass traps behind and absorption all over the place and an acoustical soffit system. But this room is tiny. That I'm standing at the back of the room. I mean, and the low frequencies are accurate, really accurate, and they're punchy. There you go. You can really see I'm the person in the back. So you're only about 6 feet behind the person sitting at the mix. And people sit there all the time and they can monitor. Can they monitor as well as the person in the front? No. But what we're trying to do with these asymmetric sidewalls is get the mix position to have the lowest variance in frequencies. Look at Tyler. Tyler, I wonder if he's on here. Anyway, it's a fun picture. All right, I think that's any last questions? Let's see.
We have James asking, have you ever integrated active acoustics into your designs? Active Strinov process and PSI AVAAs or equivalent? Your angle on cyst, talking
Yeah,
control room.
it's funny. I've set up a number of turn-off systems and gone in and tuned them, and I can always do it better than their automated process. Same thing with Genelec. I let the client decide. You know, I said, you listen to it, bring whoever you want, and you make the decision which one you like more. And I always win because the human experience can't be, you know, analyzed and tweaked perfectly without a lot of experience and critical listening. Um, you know, it's funny because some of the guys in this, like this gentleman who's a up and coming rapper, really, really great ear, man. This guy's got an amazing ear. We had so much fun listening to it. I played music that I knew, he played music that he knew, and we'd find things in common. And it was really fun. But the thing is, the room's accurate. So both of us could enjoy the tuning. You know, it's a process. When I think about what's going to happen in a room, I think about what's going to happen plus. So for equipment, we always put in extra conduit because it's so cheap to put in when you're building something and so expensive to go back and put it in later and have to stop your operation and open up walls. Big pain in the ass.
Absolutely.
And let's see. How do you deal with very uneven left-right reflections in a room where one side's glass and the other is not? Same way I just showed you. I tilt glass where I can. I'm trying something new. We're going to use the glass absorbers and base traps in a new project in New York City. I'm really excited about that. Uneven left-right reflections. Well, then you're not designing the room, then you're patching the room, right? I mean, if you have uneven left-right reflections, look at the surface and see what treatment will make it more even, right? I don't know what else to say about that. Is there anything else we can say? Oh, I can control this. Like books or schooling as far as materials and frequency response in recording studios. Martin, most manufacturers will give you data. One of my favorite things to do is look at the absorption coefficients and see how they wrap. You can see this, correct? If you look at the 250 hertz number for 1 inch of duct liner board, it's 0.3, which is half of the 500 hertz absorption, which is 2/3 of the 1K absorption, which is 80% of the 2K. And if you go to 125 hertz, it's doing essentially nothing. So when you get up to 2 inches and 3 inches, these numbers all go above 1 and you're still 50% apart, but you're so much better than you were when you were only 25% or 50% apart, or I'm sorry, 25% represented here where you're 50% represented between 2 octaves. So the 3-inch gives you much better treatment. So learning how to read these is really a skill. I always check the 1K, the 500, the 250, and the 125 because I want at least this, if not better. Where can you learn? Simon says he meant live rooms where recording musicians is done. I'm not sure what he was asking there. James said, James Bond, that's great. I think you're saying the second. I think you're 007 should be James Bond 007. Dave Airshow is a fantastic room with Dave performing miracles. Yeah, he's really good. Makes me look really good because he keeps his gear pristine. Have you ever used integrated active acoustics? I don't like active bass traps. Active, the Trinoff process. I've played with all of them and I'd rather just do it myself. It's faster and it sounds better. I can beat those, but they're getting good. I have a question regarding modes. Sam said he measures modes, placing a microphone on the corner of the room, and he uses a sub. Is there any other way to do these measurements when a sub is not available? I've heard placing a loudspeaker in another corner of the room and try and enhance its lower. Yeah, I mean, if you want to make a good measurement, you need source material at that frequency. Bring a sub in. I mean, small subs are easy, or bring a 15-inch driver and boost the hell out of the lows and don't blow it up. Or if you do blow it up, don't say that I told you to do it. When designing, there are some specific mic locations or design generally good room and mic placement is then part of the creative process. Both. We look at what happens with sound sources all over the stage. We put a grid and we run simulations of reflections all over the place and try to look for bad reflections. Also, floor reflection from musician to microphone, is it a problem? No, not at all. Can I treat a shoebox A room with concrete walls, knowing that every wall resonates at different frequencies? The walls aren't resonating. The air inside the walls is resonating if they're well-built concrete walls. That's Simon Wasif. We have two Simons. You can treat shoebox wall with absorption, diffusion, or you can angle walls inside of it. Those are the only three choices you have. Have you designed an acoustic room like no wall panels? I don't know what he means by nut corners. I'm gonna have to find out that. I have not written books about acoustics. I have two that I'm writing now. And I'm so friggin' busy, I don't get to do it as much as I would like. We have some new messages.
When are you planning to
No one,
release them
no
though?
one I
That's the
know, no one I know. Hey, there's Christian. Hey, Christian, I hope you feel well credited. Any software for absorption, efficient, and RT prediction? We've got all the software and spreadsheets, and we just use whatever's at hand and we feel is appropriate. I don't even know what to say about that. RT prediction doesn't really matter to me, except for the difference in power. That's about it. You guys all good? All right, so here's the deal. You guys are like stayed here a long time and put up with this incredibly long thing. And what I'm going to do now is be responsive to this. What the hell just happened? Can you still see me?
yeah, absolutely, absolutely.
Great. Where'd my teams go? All right, great. So that's not what I want. Where'd my team's meeting go? Well, I don't know where it all went, but it's not here.
Try doing with the command tab. Maybe you'll find it with the logo.
Yeah, I'm looking. Anyway, what I was going to say that I think is interesting is, guys, you know, we have a Facebook group called Acoustical Construction Details and Discussion. You can send me a direct message. You can text me. You can call. You know, I work a lot, so I can't answer. All I ask is that you try to answer your question before you ask me. If you spend 10 minutes trying to answer your own question, most of the time you can. If you can't, send it to me and I'll try and get you an answer. I can't promise it'll be quick, but I'll promise